Okay, welcome to an important session. We're going to be covering asymptotes and wholes, and as you see, I've marked it very important. You're going to have at least two MCQs on your test about this, and FRQ1 is also based on asymptotes and wholes. So it is an important topic, so let's dive into it without wasting time. Let us begin. A vertical asymptote. It says that an asymptote is a line whose distance from a curve approaches zero, okay, as the curve tends to infinity. It also states that a rational function has a vertical asymptote at a value of x for which the denominator evaluates to zero. Keep this in mind, okay? The denominator evaluates to zero, but the numerator does not evaluate to zero. That is the key point, okay? And I'm going to show you what it looks like graphically. So, for instance, if you have a graph like this, okay, these are the x and y axes, and it says that a vertical asymptote is a line, okay? Let us assume the line to be x equal to a, okay? This is the line x equals to a. This is the point a. X is a. Now it says that as the curve approaches, okay, I'm gonna draw the graph now. For instance, if from the left-hand side, okay, it goes like this, it's coming, then it goes down, 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 okay? And then from the right hand, up, it comes here, and it comes close, 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 close. What you observe is that it says that the curve approaches zero. It does not become zero. For when your curve is coming right down here, okay, it's gonna come closer and closer to your green line, but it'll never make the green line, okay? You're running and running and running, but you won't make the finish line. And the same thing is seen from the right hand side. You're coming closer and closer to the green line, okay? You're not coming at it, okay? You're just coming close to it, but you're not at it. And that is what the limit notation precisely explains. It says that if the limit as x approaches a, okay? The limit as x approaches a, from the right hand side. If you look at a tiny plus or a tiny minus over here between the function and the limit, a positive sign indicates coming from the right, and a negative sign indicates coming from the left. So coming from the right, the limit as x approaches a, coming from the right is positive infinity, and the limit x approaching a from the left hand side of f of x is negative infinity. Now, it's going to be more clear with the example that I show next. We have an example here where we're supposed to find the vertical asymptotes. I'm going to start by writing it down. We have x plus 8 times x minus 3 upon x squared minus 5x plus 6. Now, whenever you're trying to find out the vertical asymptotes, make sure that your numerator and denominator are both in the factored form. Over here, you'll notice that your numerator is in the factor form, but the denominator is not. Okay, this needs to be factored. So we're going to work on that. We have x squared minus 5x plus 6. Okay, we know how to factor that. We have x squared minus 2x minus 3x plus 6. I'm going to take the 3 from here, and I'm going to take the 2 from here. We have x into x minus 2 minus 3 into x minus 2. And what we get is x minus 3 times x minus 2. Now that it is in the factored form, I'm going to put this back over here and get our new function. We have x plus 8 times x minus 3 upon x minus 2 times x minus 3. Now, here is a part where most of the students will make their mistake. Some of them might be tempted to cut this off. Okay, cut off the x minus 3 and work with the x minus 2 and x plus 8. So we know that the vertical asymptote states that the denominator should tend to 0, okay? This guy should tend to 0. but the numerator should not tend to 0. The denominator is 0 for x 2, 3, okay? When x is 2, it's 0, and when x is 3, this guy becomes 0. So what you need to look out for is that it also says that the numerator should not be 0. In this case, if you put x is 3, this guy will tend to 0, but this guy along with it will also tend to 0, which is not what we're looking forward to. We need this guy to stay not equal to 0. So we have to discard 3 as a vertical asymptote because both the numerator and the denominator tend to 0. When we choose x as 2 though, this guy does tend to 0, but this guy up here does not tend to 0, okay? So finally we're going to state that our vertical asymptote is that x is 2 because this guy tends to 0 and this guy does not. I hope that was clear. Let's move ahead. Now time for horizontal asymptotes or the end behavior. It says that, I'm going to get my pen. It says that the end behavior of a rational function will be most affected by the polynomial with the greater degree, as its value will dominate the values of the polynomial for larger magnitude inputs. So what the horizontal asymptote is about that, you want to find out if you put x to infinity, okay, what happens to the function? Does it turn 0? Does it also go to infinity? Does it become undefined? That's what the horizontal asymptote is about finding, okay? When your x turns to infinity, what happens to your f of x? What happens to your function, okay? And what you have here is the general notation of a polynomial, of a rational function. an here, and bn. And these are the leading coefficients. So we have an into x to the power n, bm x to the power m, and then we go on decreasing the powers and the indices till we have a naught and b naught, or a0 and b0. There are 3 cases. We're going to work on them one by one. Let's move ahead. Before I move on to case 1, I want you to understand that whenever you're dealing with horizontal asymptotes, the only thing you'll be concerned with and the only thing you'll be looking at is the term with the highest power, or the degree. For instance, if you have x to the power 3 minus x to the power 4 plus x squared, the only thing you'll be concerned with is the x to the power 4, ignoring the rest of it, because as we increase the value of x to the power 4 will dominate the rest of the term. So here it says that if n is less than m, okay, if the degree of the numerator is less than the degree of the denominator, then the rational function has a horizontal asymptote at y equal to 0. If you look at the example, phi x upon x squared minus 9, you'll see the degree, or n, over here is just 1 because x to the power 1 is x, and you'll find an x squared at the bottom, so you have m as 2. Now since n is less than m, we have a horizontal asymptote at y equal to 0. Let's move ahead. Now the second case says that if n is equal to m, which means if the degree of the numerator is equal to the degree of the denominator, then the rational function has a horizontal asymptote at y is equal to an upon bm, which is the division of the leading coefficients. If you look at the example we have, that says 3x squared minus x minus 4 upon 2x squared plus 5. We realize that the leading power, which is the degree, is 2 over here, and so is it over here. Since we have n is equal to m, which is equal to 2, our horizontal asymptote will be an by bm, which in this case is the leading coefficient of x squared, which is 3, upon the leading coefficient of the denominator x squared, which is 2. So we have a horizontal asymptote at 3 by 2. Let's move ahead. Now case 3 says that if n is greater than m, that is the degree of the numerator is greater than the degree of the denominator, then the rational function has no horizontal asymptote. End of the game. If n is greater than m, there is no horizontal asymptote. That is what you should know. But the test may ask you to find the end behavior, okay? They may ask you to find the end behavior, and in that case, we have this point. The end behavior asymptote is the quotient polynomial that is found when the numerator is divided by the denominator. If that polynomial is linear, then the function has a slant asymptote parallel to the graph of the line. For instance, in the first example, you'll see x to the power 3 upon x squared minus 9. You know n is greater than m. You divide them to probably get, we'll have an x, and then we'll have a 9x up here upon x squared minus 9. This is a quotient polynomial, and this is a remainder. And it says that if the quotient polynomial is linear, then the function has a slant asymptote. Since x is linear, x to the power 3 upon x squared minus 9 will have a slant asymptote that is parallel to the graph of the line. In the second example, we have x to the power 3 as the degree and the leading coefficient. And we have an x upon 1 in the denominator. Now, if we divide this, I'm not sure, we should get x squared minus 2x plus 1 plus, we'll have the remainder as 2x minus 1. This is again your quotient polynomial, and this is a remainder. And since the quotient polynomial is not linear, this is a slant asymptote, or this is the end behavior that's going to work for n is greater than m. So let's move ahead now. What we're going to discuss now is called a hole, and this is very important considering that it is very similar to vertical asymptotes, and people often mess up holes and the vertical asymptote. So I want this to be very clear. It states that it's also called as a removable discontinuity. There are two steps: first to find the x-coordinate, and second to find the y-coordinate. It says that we're going to completely factor the polynomial first. We're going to remove the common factor, okay? Remove the common factor, and the zeros of the common factors represent the x-coordinate of the whole. It's going to be much clearer when I show you this with an example. And to find the y-coordinate, after removing the common factor, we substitute each x value of the wholes into the remaining factors of the rational function, and the solutions that we get are the y-coordinates of the respective x values. Let's move to the example. If you look at the example that I have here, we have x plus 8 times x minus 3 upon x squared minus 5 times x plus 6. If you notice, this is the same thing that I showed you for the vertical asymptote. So I won't waste time factoring this out. Rather, I'll write it directly. We have x plus 8 times x minus 3 upon x minus 2 times x minus 3. Now we know that there is a vertical asymptote at x equal to 2, and we discarded 3 because it turned the numerator 0 as well. Now in the whole, what you do is that you cancel out the common stuff. We have x minus 3 common here, and we find out the zeros of the common factors. So x minus 3 has to equal to 0, and that'll mean x should be 3, basic math. And now, since you know that x equal to 3 is the x-coordinate of the whole, we're going to put x is 3 into the remaining factors. We have x plus 8 upon x minus 2, and when you put in x is 3, you have 11 upon 1, which is just 11. So the whole has the coordinates 3, 11, since this is a 0 of the common factor, and this is the output when you put in the zeros of the common factor into the remaining polynomial. I hope that was clear. I think that was it. Thank you, and we'll meet soon.